Good morning or good afternoon, everyone, depending on where you're joining us from, and welcome to today's webinar. My name is Freddie Lawton from Business Review, and I will be your host. It is our pleasure to have Perstorp with us today. We'll be discussing cationic UV curing coatings and inks for packaging. Today's guest speaker is Paul Kelly, who is the Technical Market Development Manager at Perstorp. I'd like to welcome you to our webinar platform On24. You'll notice that this webinar is browser-based, so if you disconnect for any reason, please just click on the link that you receive via email to rejoin the session. In order to ask questions, you can send them in via the questions widget. Just type them into the box at the top left-hand corner of your screen and click Submit. We will allocate around 10 to 15 minutes at the end of the session to address any questions or thoughts that you may have. Please use the yellow Help widget if you require any assistance, and you can move, resize, and maximize any of the windows in front of you to get a better view of the slides. But now, please allow me to welcome Paul.
Thank you, Freddie. And welcome to everybody who's listening. I'm honored that so many of you signed up. The title of the presentation, Packaging Design and Cationic Curing Materials, is meant to place packaging design and cationic curing coatings and inks alongside each other so that we can properly look at the merits of the technology with respect to practical demands. Incorporated in the presentation are some poll questions which could help me to tailor the presentation to the audience that we have. And since we have quite a large number of participants from a wide range of backgrounds, it'd probably be difficult to make the presentation perfect for all. I'll do my best to pitch for everybody if I can. And in that case, I wonder, could you please let me know, do you have some chemical knowledge? Please answer yes or no. I've not put a lot of chemistry into the presentation, but just that answer should help me a little bit. Okay, it seems that predominantly we do have some chemists among us. About 80% answered yes to that question, but we'll try and be kind to the other 20%. And anyway, it's the principle of packaging and cationic cure working together in a design concept that I want to really consider at the top of everything. Firstly, a quick introduction of who you're listening to. That's me. I don't want to go into any great length, but so you know who you are listening to. I've been working with radiation-cured, that's UV and EB coatings and inks since 1981, 35 years, hardly seems possible. I was first a formulator, spending 19 years at a number of inks and coatings companies, and I then went on to work for 12 years at resin manufacturing companies. I started my career in metal decorating, actually. Most recently, I've been 4 years at Perstorp. As Freddie said, I have the position of Technical Development Manager, and that means I'm part of the innovation team, and I have specific responsibility for all of our products that end up in some way in RadCure applications. I have strong connections with the RadTech Europe organization, and I'm a member of 2 of the committees, including the marketing committee. And I was part of the conference organizing committee for last year's conference in Prague. I'll take a moment just to introduce Perstorp for those of you who may not know who we are. Perstorp's a company that employs approximately 1,500 people in 22 countries. It was founded in 1881. The chemistry of Perstorp originally came from the forest. It's a Swedish company. And we've been a pioneer in formalin chemistry and derived products. We have a commitment to sustainable products, and we have a history of innovation. We've been involved in the RadCure products and the RadCure technology for many, many years as a raw material supplier of intermediates, particularly for acrylate materials. We have 9 production units in Asia, Europe and North America, and we also have a sales hub in each of the 3 regions. and sales offices in all major markets. So along with 50 agents and distributors, we're pretty well everywhere you need us to be around the world. Okay, I'll take a moment to introduce the scope of the webinar now. I'd like to start by just summarizing the content. And the main theme is we want to make a connection between the demands of packaging, that is technical requirements, aesthetic requirements, and the technologies that are available for decorating the packaging. And particularly the focus of the presentation, as you picked up from the title, is to consider cationic curable radiation curing inks and coatings. I have a strong feeling that while radiation curing is in the minds of packaging designers, the term might not necessarily differentiate very well. And I wonder if cationic curing is very well known among brand users, formulators, and packaging designers. Maybe it is. There's a poll question which can answer that question coming along soon. There's a lot of historical baggage as well, which at this point I would ask you please put to one side if you have any previous sort of bias towards or away from one technology or another. A lot of the history has been difficult, and I'll tackle that as we come to it. We're going to focus on flexible packaging, cartons, and metal decorating mostly. And I'll take a quick look at a comparison of other available technologies, such as solvent-based and water-based inks too. One of the most difficult areas for packaging is for food applications, and in amongst all that I would add pharmaceutical products and tobacco products, since all three of those place a severe demand on packaging in terms of migration and organoleptic, that is, odor and taste properties. The term functional barrier is also important here, and different packages either have that or they don't, and we can design around what that means with the decoration in many cases. So what I aim to do is to show how cationic inks and coatings offer solutions to packaging problems based on real-world examples. So now the poll question I referred to. I would like to ask you, do you have any experience of radiation curable coatings and inks for packaging? It's quite a wide range of participants I saw in the list, and radiation curing is perhaps not a term that's familiar to everyone, and I would like to take a moment to explain it if necessary. Please answer yes or no. Okay, that's interesting. There's over 50% not really with any experience of radiation curable coatings. We have about 35% who do. So I'm going to now move along to a little bit of a discussion of the different types of packaging materials, and we'll come to an explanation a little bit of what radiation curing can offer, and particularly what cationic curing can offer. If you consider the different types of packaging materials, there's an enormous number, and I really can't hope to cover everything in an hour. Metal decorating, for example, has problems associated largely with mechanical properties. Metal does work as a functional barrier in food applications, but some contents, for example, sugary beverages, are very aggressive and can even eat through steel overnight. I started my career, remember, in metal decorating, and we used to do a test putting metal in contact with coatings on and in contact with various sugary drinks that I shouldn't name. And it always amazed me that overnight at 50 degrees it would eat straight through pretty well all sheet steel and aluminium that you put in the way. Cationic curing is already used in metal decorating. It has a strong position as a coating for the bases of beverage cans due to its resistance properties. It can resist a certain amount of mechanical damage, for example, in shallow drawn food containers. And it's possible, if we spent some time to look and formulate specifically, that it would also be suitable for things like ROPP, that's the roll-on pilfer-proof caps. Those are the caps that the stronger beverage drinkers among you, people who like their whiskey, wine and spirits, will be familiar with. They're the ones that snap when you open a new bottle. It's the security cap on top of the bottle. The picture's there on the screen. Moving on to plastic packaging, and there are so many forms of plastic packaging, from rigid cosmetics containers to flexible films, semi-rigid plastic tubes, etc. for toothpaste and the like, some of those laminated. And cationic curing holds a niche in plastic packaging too. It's used on shrink sleeves, it's used on the skins that wrap preserved and cured sausages, and it's used on bottles that hold aggressive contents like gear oils, for example. Glass. Most of the problems associated with glass relate to the problem of adhesion and the processing, where a bottle might be washed or boiled, and the fact that in many cases there are multiple materials used in a glass pack. And the last one I have on the screen is cartons and board, paper labels, cartons and laminates. The picture of the egg, by the way, is a case of double packing, where nature tried first but made it very difficult to stack on shelves. So we end up using a second package, in which case, again, the decoration is part of the package. And it's worth remembering, as I mentioned briefly just then, that many packages are made of multiple materials. So in the design of a pack, you have to consider the whole pack. Okay, so now if we look at the materials that are available, I said it before and I don't want to repeat myself too much, but the range of materials is vast. If I only considered plastics and metal, as I've shown on the screen there, I can easily name 18 different cases, each with individual problems associated. They're not all that common, some of them, but they do arise. And we don't choose a packaging material to cause problems, we choose it to solve packaging design problems. But there's no getting away from the fact that polyolefins like polypropylene, untreated polypropylene, and PET present completely different properties to some of the other plastics on the screen, like polycarbonate or ABS, for example. And in the case of metal decorating applications, just considering aluminium on its own, or aluminum to the American listeners, we can identify the end uses that include the use of multiple materials, the sterilization in the processes, there's some severe flexing and distortion of the substrate, which the coatings and inks must follow. In the case of tubes, for example, for glues and adhesives, there's crushing tests, there's temperature cycling, and you could go on and on and on, but I won't. So, first thing I should emphasize, and I really believe this strongly, is that packaging decoration should be considered an integral part of the packaging design and should ideally enhance the properties of the package. There's so many different things to think about, and each package is different. I look at the list of listeners in this presentation, and I think some of you have far more expertise than I do. So I'm going to come to this from the point of view of someone who has some limited packaging knowledge of design, but a lot of experience tackling the problems that are caused by trying to pair decoration and materials. So some of the things that have to be considered: there's adhesion to the substrate. The decoration's got to be adhering to the substrate for the useful life of the package. Now that can be quite short, but it's got to be stuck and it's got to stay there. The range of substrates is extensive, as we already said, so it's unlikely that you're going to have one ink or coating that's going to be universally suitable. Second thing, aesthetic properties, gloss, clarity, color, etc. That can be an enhancement in the decoration, or if you get it wrong, and something changes to a matte finish when you pasteurize something, you're on a problem. Mechanical properties and chemical resistance. Flexibility, especially in the case of the metal decorating and the flexible packaging, extensibility, scratch resistance, impact resistance, heat resistance. You could go on and on. Again, I won't. And all of this is not only resistance to the world and the environment outside, but also very often the contents and the processes that the package goes through are very aggressive. So we have sterilization, for example, to cook the foods inside the package. And we have, as I mentioned, gear oils and the like, which are very, very aggressive. We have to pay attention to make safe packages. We choose safe materials. We avoid heavy metals, for example. If you're packing toys, it would be a bad thing. We avoid toxic materials. For food packaging, we have to consider things like the extraction, migration, and the organoleptic properties of the materials that we choose. And we have to consider, can the decoration and the package together also contend with hazardous contents, strong alkalis, strong acids, etc. And it's worthwhile to consider that some coatings and inks are very functional in other ways. For example, tamper-evident security inks, or even temperature-indicating inks. I remember being associated once with a chocolate biscuit that wasn't selling very well in the summer. And the idea was taken that it would be great if we could convince people to store them in the fridge by having an ink with a prize revealed if people reduce the temperature to 4 degrees, which we did. And a packaging design then became a marketing point and a sales tool. And lastly, we should consider environmental concerns, recycling, sustainability, green credentials. I'd like to ask you at this point, what type of packaging are you mostly concerned with? There's a wide range of people here attending, and it would be interesting for me to know if folding cartons, paper or plastic labels, glass, metal, plastic containers, or flexible packaging is predominant among you. I see from the companies that some of you come from, I could probably make guesses, but much better that you can give me an indication yourselves. And this is for my interest again, so that as I go forward, I can make more or less emphasis and use the time a little better. Okay, so predominantly flexible packaging. We have over 60% in flexible packaging. Small number in glass, less than 10%. Around a third each for folding cartons and paper or plastic labels. 43% for metal and 43% again for other types of plastic containers. So a fairly broad split, actually. I'm sorry, by the way, if I left off anything that you spend your lives working on and I forgot to mention. But that then takes me on to the next slide, which is, okay, so we have the materials we've considered, and now we're starting to consider how do we decorate the package. So no matter what type of package it is, we have the first choice, which is to directly print or coat straight to the substrate. The second choice is we can use a label, adhesive, plastic or paper label. We can use shrink sleeves, in other words, a secondary decoration on another substrate which is applied on the first. And the third choice is that many packages are made with mixed materials, and so therefore we could use some part of the package as a site for decoration as well. In all cases, whichever of these choices we choose, the decoration is normally applied with one of the following techniques, and that is solvent-based or traditional oil-based materials, water-based coatings and inks, and that includes emulsions and dispersions, and also to a smaller extent water-soluble materials. And the one I'm most interested with today is radiation curing materials. In fact, radiation curing materials, or RadCure as it's often abbreviated, includes three general styles of materials. One is UV cured free radical materials. The second is EB cured free radical materials. And in fact, they're pretty much the same, those. The same constituent acrylate materials are used. UV includes an initiator which interacts with the light and sets off the reaction, whereas EB, electron beam curing, doesn't need the initiator because the electron beam generates radicals which continue the reaction. And the third choice, which is the one I really want to focus on because I think it's a neglected art form, you could call it, is cationic curing. And as we go through the presentation, I hope to show that cationic curing has a very strong future and even now is growing a little. Okay, I'm going to linger a little bit more on this slide than some of the others. I don't want to bore you, but this is critical to how we start with the choice of decoration materials. And by considering the strengths and weaknesses of each possibility, it's possible to make a short list of candidates. And so I want to just discuss briefly some of the strengths and weaknesses of those three technologies that I mentioned for decoration. In fact, this could be a cause of some argument, as most of these could be subject to disputes at some stage or other, depending on the experiences you might have had. I don't want to be negative towards any technology. Perstorp has interests in water-based, solvent-based, free radical UV curing, and in cationic curing. So it doesn't do me any good to do that. I just want to be objective. In the beginning, there were oil and solvent-based inks and coatings, and my career coincided with the early days of RadCure and water-based technology in the 1970s and 80s. And at first, those started to create a niche, and then slowly over time, they've created a more expansive position, and they become something that can be considered in their own right much more. Solvent and oil-based products, they come in many forms. It's difficult to generalize here. For the purpose of this presentation, I'm including oil-based litho inks, nitrocellulose gravure inks, 2-pack isocyanate-based lacquers, all in one group. And so the strengths and weaknesses are a little bit of a generalization, but I have to try and contend for this within the hour the best way I can. To consider the advantages of the traditional technologies, the first one is pretty obvious to me, is that the length of the history. People have been using conventional traditional technologies for much longer than I've been alive. They're generally quite low cost. Not always, but as an option, it does tend to be the low-cost option. And because of the long history, there's a massive range of available materials to choose from. They can be made resistant, though not always. They can be very poorly resistant too. They can be low odor, like NC inks for cigarette cartons, for example. But there can be big problems associated with odor in other cases. They've got very good flexibility and adhesion characteristics, for example, when stoved and used on metals. And they can be made to be cross-linked and become quite chemically impervious in the case, for example, of 2K systems. But, and this is where we come to it, there are some very big general weaknesses associated with traditional materials. I presume everybody's heard the phrase VOC, volatile organic compounds, and in most of industry we're trying to reduce VOC content in pretty well everything, all coatings, inks, paints. VOC, volatile organic compounds, that's enough of a reason for people to want to look at alternative technologies. The majority of solvent-based and oil-based inks and coatings are based on fossil-derived chemistry. That's partly true as well for water-based and RadCure, but the elimination of the fossil-based solvent content, the VOC content, means that the advantages of those other technologies is quite large. In case of inks, we could talk about soya-based inks, but there are problems associated with all of these technologies in terms of drying, etc. And there's a second big hit with many traditional solvent and oil-based technologies, and that's the fact that it needs very often an oven for drying to drive off solvent, and the solvent has to be collected somehow from the ovens, or in the case of inks, to make things oxidize. And so the oven or the heating component adds a significant energy component to the processes involved in making a package. As I said, there's a good history of nitrocellulose-based gravure inks to give low migration, but in the case of many oil-based litho inks, for example, migration is a big problem, and so packaging designers are trying to move to low migration constituents for food packaging. Moving on to water-based, and in this case now I'm going to talk about the advantages and disadvantages compared to radiation curing as well. Water-based, it definitely sounds sympathetic, doesn't it? Water, it has a name which sounds environmentally friendly straight away. Certainly much better than radiation, as in radiation curing. But that's not the whole story. Think about taking your holidays. Light is radiation, and I'm sure we're all happy to go on a sunshine vacation, and we'd still be happy to take the vacation if we called it a radiation holiday. It's the point that radiation is just a name. Still, water has a safe image that can't be denied, and it's very often justified, but not always. Much of the chemistry of water-based coatings isn't so different to the majority of UV chemistry, actually, based on acrylates. If surfactants and coalescing solvents, stabilizers are added into the mix, the case gets very complicated. But for the most part, water-based coatings have many advantages over solvent-based products, and should definitely be considered in a lot of cases. The big downside, mind you, with water-based coatings and inks is the fact that the majority of them are only about 40% solids content. The rest's water, and that needs to be removed. And that isn't easy to do in a lot of cases, and it means there's also a need for some sort of drying by infrared lamps, ovens, or hot air blowers. And the low solids content means that you only get value from less than 50% of your formulation. And that part of the cost comparisons is sometimes overlooked. Because of the water content, water-based coatings are not suitable for some substrates due to adhesion restrictions or other reasons. I don't want to overstate the problem, but water-based products on impervious substrates can present problems in terms of the quality of print and also the adhesion characteristics. For food packaging, water-based formulations have a very good reputation for low odor and migration character, but it doesn't have to be assumed. Some of the components of the coatings and inks can cause problems if poorly chosen. Things like amines, for example, and the coalescing solvents can crop up and cause a problem unexpectedly. If we consider radiation curing or rad-cure coatings and inks, there's one major advantage over the other two technologies. It's VOC free, and it's normally 100% non-volatile. You use what you pay for. The cured solids content, as we refer to it, means that you can pay more than twice the price for a UV coating and get the same dry price as a water-based one. The quality of finish of radiation curing inks and coatings is very desirable, especially if you want high gloss. There's really not another technology that can match it. Rad-cure is fast drying and can be processed immediately after printing. In other words, subsequent package processing, cutting, creasing, gluing, that sort of thing can be done very, very soon after application. So production speeds can be fast, and the drying is done with light, so the process is relatively low energy, especially now there seems to be an advent of LED curing lamps, which are particularly low energy content. Lamps are compact compared to ovens, and that means that you have a tendency towards space saving. You can often retrofit lamps onto existing machinery, although I do recognize that there can be difficulties retrofitting on common impression gravure machines, for example. Contrary to popular belief, it's possible to formulate low migration and low odor radiation curing inks and coatings. though you do have to take a lot of care in choice of ingredients. In the case of acrylates for free radical curing, the considerations to make regarding irritation, labeling, etc. But that's less of an issue for cationic curing. The same can be said for the belief that UV curing materials have poor adhesion to difficult substrates. Sometimes they do. Actually, RadCure, both types of RadCure technology can adhere very well to some substrates, but cationic inks are exceptional and have adhesion properties which make them specially suited to some uses. As with all the other technologies, it's important that the application and curing equipment is kept in good condition and kept at an optimal working usefulness. It's no good running your machine for 5,000–10,000 hours and expecting the lamps to be as efficient as they were when you first bought it. Okay, so I'm now going to move on to consider the RadCure market specifically, and then we'll take some examples of some real-world cases where cationic curing is particularly suitable. This slide that you can see now is taken from the RadTech Europe organization and shows a rough overview of the worldwide usage of RadCure formulations. In our case, we're interested in a portion of the industrial coatings, almost all of the OPV, that's overprint varnish part there, the OPV lacquers, and nearly all of the printing inks. So all in all, that's about 45%, or around 250,000 tons, and a large proportion of that is packaging. Remember, this is the whole market, so it includes things which are not necessarily packaging. The fastest growing portion of the RadCure market is in packaging, and I have to say as well that RadCure coatings and inks are growing faster than the other technologies I've mentioned so far. I have to pause again at this moment because I'm about to separate the two types of RadCure technologies. Obviously, those of you who answered no to being familiar with RadCure generally probably will answer no to this as well. But there are two distinct technologies, as I mentioned. One is free radical and the other is cationic curing. And I wonder, are you familiar with the difference between those? Okay, so the majority not. We're about 85% say no, they don't know the difference. And this sort of confirms a suspicion that I had in that brand owners and packaging designers, they understand that UV and radiation curing exists, but not necessarily the nuance, which is the suitability of each technology for certain packaging designs. So this looks like a chemistry slide, and I promise you I won't make too much of it. This, for those of you who already know the chemistry, you will recognize shows one of the fundamental differences shows the difference in the chemistry between the two types of technology. RadCure, radiation curing. Free radical curing, that currently holds a position of around about 95% of all the radiation curing that's in the market, whereas cationic curing is only around 5%. And I would say that's probably one of the biggest differences between the two technologies. Why is that? Well, the reasons are historical, and I'll try and summarize them quickly. It's a little like the story of Betamax video, which I'm old enough to remember, which was arguably a better format for video, but it lost out to VHS in the 1980s, and I told you I was old. The result, I fear, is that when a brand owner is designing a package and raises the possibility of UV curing decoration with his or her supplier, there's a tendency for packaging suppliers and designers and fabricators to default to what they already know and what they're familiar with. And if 95% of the market is free radical, I suspect that cationic curing is being badly overlooked, despite some major technical advantages. Unfortunately, if we constantly default back to the majority, then it becomes self-fulfilling a little bit. So I'm not going to linger too long on this either. The history of cationic curing is a little bit checkered and tarnished. And the reason it fell into this Betamax situation started way back at the birth of the technology, when there were patents held by 3M and GE. Now, to pay royalties on those patents was quite expensive, and it meant that a lot of developers in those very early days developed materials for acrylate chemistry, free radical chemistry, rather than those, just to avoid the royalty payments. Later, Union Carbide came into the market, and they brought to the market a range of materials called Cyracure, which were rebranded actually. They had limited success, and the idea was that royalty payments would be paid as part of the cost of the materials. But it was so complicated at that time that a lot of people didn't take it up. Further to the question of the patents, at one point there was really almost a single supplier of the epoxides that make up the majority of the formulations, that being Dow. And you can imagine a single supplier situation, royalty payments to pay, and a lot of nervousness arose in the markets. And eventually, in somewhere through the 2000s decade, Dow exited the market, and that meant two things. It meant that we needed new suppliers of the epoxies, and also that the prices went through the roof at that time, and it gave a reputation to the technology of being expensive and difficult to sustain. There were some specialty formulators who found a very good niche in Cationic, but some of the bigger companies and formulators decided against. There have also been, down the years, a number of scares surrounding some of the initiators. At one point there was an initiator that contained the heavy metal antimony, and there is the truth that certain cationic initiators can theoretically release benzene in the curing process. But, and this is important, both of those problems, in fact all of the problems I've shown on that page, are now solved. Unfortunately, the legacy means that we're now at a chicken and egg situation where the lack of use keeps the costs high, and if there's more adoption, then costs will come down and there will be more materials. So the time is right for cationic curing, and in fact, for reasons not necessarily related to packaging, in fact related to a lot of Asian electronics adhesives markets, we're starting to see a growth in cationic use around the world, and we are seeing a tendency towards slight lowering of prices. The thing to emphasize here, though, is not the prices, not the costs, because they do have a niche that makes them commercial in some cases, and I'll show examples, but the fact that cationic curing has some very big advantages and can solve a lot of packaging design problems. Okay, so I've said there's two types of UV curing technology, and you probably wonder, apart from the chemistry and the different sizes of the two technologies in the marketplace, what are the advantages and disadvantages? So here I come to the point and say that UV curing generally has some well-known advantages. It is incredibly space efficient. Space saving from UV curing is incredibly good, and retrofitting, as I say, is a possibility. Speed of cure is very, very attractive. In the case of acrylate curing, speed of cure is in seconds, in fact fractions of a second. UV curing can be used by pretty well every application technique, from gravure to screen print to lithography to flexo to roller coating, Analox rollers, opti-rollers, you name it, curtain coating, it's used every which way. Now, especially today in digital print, and if the digital print takes off in the way that some of the makers of digital printing inks are hoping, then packaging by digital print will be the next big explosion in the market. Okay, so those attributes are well known and sought after, but free radical curing also has some disadvantages. Some of them are perceptions, actually, more than real true disadvantages, but I'll name them anyway. Although it's 95% of the market, it's perceived as being unsafe in some cases due to irritancy labeling on the monomers. And since the oligomer content, that is the resin part of the formulation, is often quite high viscosity, then the diluents, the monomers that are used to reduce viscosity, can't be avoided. And if we retain the 100% solids VOC tag, then it's difficult to move away from some of the irritant monomers that are causing problems in people's perceptions. Actually, if the right types of handling precautions are taken into account, there's no reason that this can't be used. And in fact, specialist UV houses have no problem at all. Free radical curing is almost instantaneous. It's a fraction of a second, but the reaction stops immediately the coating comes out from the curing source, the light. Therefore, there can be uncured fractions left in the film, and that can be minimized to give low migration and coatings, but it's not totally cured in many cases, so we tend to want to use high molecular weight materials that don't migrate. Free radical curing is also affected by atmospheric oxygen, and that means there's a phenomena which we call oxygen inhibition, which slows the cure a little bit on the surface. There's different ways to overcome that. One of the easiest is to blanket the curing process with nitrogen, but that's very expensive and not easy to control. Second way is to include amines, which tend to work as co-initiators, if you like. But the problem with that is that they can be odorous and not great for migration. But probably the biggest disadvantage of free radical curing compared to cationic curing is that it shrinks when it cures. The acrylate curing process means that in some cases, for some monomers, there's shrinkage of up to 25%. Not for all. In fact, it can be minimized in a formulation down to 5 or 6%. But the point is that that can cause problems for flexibility and for adhesion on some difficult substrates. For example, on metals, it's very difficult to make direct to metal coatings with acrylate technology. By contrast, cationic curing has most of the advantages that are listed there, but it's got some additional advantages. And a lot of the advantages relate to the fact that cationic curing formulations don't shrink, or at least it's very minimal. It relaxes as it cures. It's a ring opening process, so the shrinkage is absolutely next to nothing, if it's there at all in some cases. The first result of that is that it has excellent adhesion on a really wide range of substrates. You can print cationic formulations direct to metal far more successfully than acrylate formulations. And therefore, it finds its niche in metal decorating. It also finds a niche in flexible films. Cationic curing is resistant to many processes and can be sterilized. If you try to sterilize an acrylate formulation, or I should say most water-based or even a lot of solvent-based formulations, you'll find that it won't pass the process, 120 degrees at pressure. Cationic curing has exceptional chemical resistance, and it's not affected by atmospheric oxygen. So the cure is consistently the same all the way through the entire film. So when you measure a cure, it's there. Cationic curing is a little bit slower than acrylate curing, but actually that's both a strength and a weakness. In some cases, for very fast applications, people perceive as a weakness, and it is possible to add synergists, and mostly touch dry is good enough off the press. and the curing then continues for about the next 24 hours. And the fact that that reaction continues means that it always goes to completion. I say always, 99-point-something% of the time it goes to completion. And that means there are no low migration fragments, and migration is generally improved. So it makes it suitable for food packaging. The other point that comes out of the low shrinkage and adhesion is the fact that you tend to get very good mechanical properties. So it's possible to make drawn containers, etc. It's not all good news. Cationic curing is hindered by amines, in fact, and it's difficult to, it's easy to avoid that just by not having amines in the process anywhere. Okay, the biggest disadvantage is the limited number of materials, but if the market does expand, as it seems to be, then that problem should be overcome quite soon. So now let's come down to what can cationic cured materials do? And what's already been done. I'll illustrate, if I can, with 3 examples which are all in the public domain and have all show problems, packaging problems that were solved and could only really be solved by cationic formulations. Okay, I found all of these, by the way, using Google on the internet, so it's very easy to find this, and I'm not breaking any sort of secrecy. The first is a Tetra Recart. Now this is a package made of carton board and flexo printed, and it's intended to contain food which is cooked in the container. It's sterilized in the container. It's the first time, so I'm reliably informed by Tetra Pak, it's the first time that this was done, the first time it was possible, and it was only made possible because the decoration on the pack was cationic cured. It's led to some amazing savings. For example, if you're transporting cooked food in cardboard containers compared to metal cans, the weight is minimal. You can transport square carton containers far more efficiently than round tin cans or glass. So cationic curing there, only possible. It's the only technology that could have done that and still have the same production speeds. The second case I'm putting up there is decorative sleeves. These are shrink sleeves for cosmetics, food and drinks bottles. The print quality has to be high. They speak of gravure quality prints, where the dots are absolutely as fine as they can be. In this case, it also needs to withstand the shrink of the plastic. The plastic is put on as a sleeve and shrink to fit the bottle. And that means there's a deformation of the cationic inks. And only cationic curing can really follow that efficiently and give cure speeds that mean the process of producing those shrink sleeves is good enough. Combine that with the resistance properties you get from cationic curing, and you have superior scuff, and you have high gloss. You have everything that you need, and only that technology could do it again. Third case is quite well known, and that is cationic curing on the base of beverage cans. I already said earlier that the acidic contents of a lot of fizzy drink cans is very, very aggressive and will eat through steel and aluminium. If there's any spillage in lines or in the shipping, for example, that drink will start to attack the base of the cans. And so cationic curing is widely chosen to coat the base of the cans to give the resistance that's necessary. It also gives slip and lubrication to the process where the cans are transported at very high speeds. I mean, above 1,000 cans a minute on rails to guide them. Okay, I'm going to go quite quickly through the next part. I just want to point out that we don't have any vested interest, particularly as Perstorp. In fact, we have a far bigger interest in free radical curing, just because of the size of the market. And our position is slightly different in the value chain. We supply to acrylate makers in the acrylate market compared to supplying direct to formulators. Being so far up the value chain, we believe that we can influence the design of materials that are available for these technologies, and we'd like to be given the opportunity to do that by getting to know the end user requirements in the packages at an early stage so that we can link the two. Okay, so we come on to food packaging. It's a complex case, as I say, because a lot of the requirements relate to legal regulations and various codes of guidance. But it's difficult to understand because it's not very well adhered to, in fact. Can I just ask how many people are involved with food packaging? What proportion of your work involves food packaging? If you don't mind just answering one of those choices from 0, less than 40%, 40 to 80%, or greater than 80%, that would be very interesting to see how much time I give to the last part of this. Okay, so most of you, I would say, well, above 50% anyway, are involved in food packaging. It looks like you either are or you aren't, because there's also a significant number who have no involvement in food packaging. Okay, so let's go into the considerations with food packaging. A little history, and I won't go too much into depth. Around 2004, in Europe at least, and I will mention the US a little bit, there was an attempt to legislate on the materials that come into contact with foods. 2005 was an interesting year immediately following that. It was particularly interesting in that there was a case, and I think it's well known that it was a Nestle carton actually, or a Nestle pack, which was found to contain a material called ITX, an initiator in acrylate formulations. I could never quite understand why there was such a problem with this, because ITX wasn't illegal. It was perfectly legal to use it. It had never been shown as harmful, and yet the public relations fallout, no matter how unfair it was, meant that the perception was very difficult to resist, that there were chemicals in packages. And as a response to that, Nestle introduced some guidance documents which coincided with Farbus presenting a paper at a RadTech conference on test methods. The Nestle guidance was being updated regularly ever since. In 2006, there was also a code of good manufacturing practice that was put into place. And the latest version of Nestle guidance refers to the latest development, which is a Swiss positive list. I won't go into the details right now, except to say that the Swiss list stipulations I can send out to anyone who's interested. Probably if you're involved in food, you already know. In the US, the situation is a little different in that we have the FDA and TSCA, and there are various statements about functional barriers, and there's guidelines especially regarding good manufacturing practice. In the US, we're now expecting to see a new improved TSCA, which means that things will change quite soon. Okay, I'm moving quite quickly on now. Just quickly to highlight the sorts of things that go into a cationic formulation. The majority formulation constituent is a cycloaliphatic epoxide. There are diluents included. These can include very many things, but the boxes shown ringed in blue are materials that Perstorp supplies. And there are particular advantages in the materials we have. TMPO, which is an oxetane, is very low odor, very fast curing compared to some options like vinyl ethers. Of course, if it's not food packaging, you don't care about odor, and vinyl ethers may be perfectly good. Initiators, I've shown one from BASF there, which they put through a lot of testing in 2011 when it was launched, and that is specifically designated for food packaging. On top of that, the same additives and fillers that are used in other formulations, and there are modifiers, and Perstorp have a range of polyols, caprolactones, and also highly functional, 10 functional in many cases, bolt-on acrylates, dendrimers. Just to show a little bit of a highlight about those that I've just said from the previous slide, the oxetane we offer is highly reactive, it enhances the performance, it's chemical resistant in combination, it's highly flexible, it's low odor, and it's safe. Bolt-on, which is our hyperbranched materials, as I say, 10 functional. That's a 10 functional polyol, which can improve cross-linking in cationic formulations. We have alkoxylates, which are safe polymeric materials, and again can give properties to the cationic formulations. And particularly kappa, which is quite a water-resistant and tough material, can lend extra adhesion to formulations. So what are we doing in the future? We're looking at currently at a methodical approach to a lab study, looking for synergies between ingredients. Our early results show, for example, that different types of oxetanes all interact with cycloaliphatic epoxies in different ways, and you can modify the cure speed by the balance of those reactive parts, not just by the photoinitiator. Now that may have ramifications for cost ultimately. I don't know, we'll have to see. If we look for a comparison of commercially available resins and diluents, we're in the middle of screening a lot of materials. I won't go too far into that now because I'm not leaving time for questions, so I'm going to quickly move on. And I would like to say there's references here which I've made to quite a lot of people who have helped me, and also documents that I've used, which are in some cases regulatory documents and such like. Okay, so now it's time for question and answers, and I'm afraid I've talked rather a lot, and I can take a lot of questions separately if you'd like to contact me. But for now, perhaps we can get through one or two questions.
Yeah, that's right. We can cover definitely a couple. So thanks a lot, Paul. Great presentation. Just a reminder for the audience, in order to ask questions, you can send them in via the questions widget. You just type them into the box at the top left-hand corner of your screen and click submit. So let's have a look. So Paul, someone says, I had heard that there have been problems with cationic initiators for food packaging. And they say, is it now safe to use cationic curing?
Yeah, in cationic curing, it really is only the initiators, as far as I'm aware, that cause the problems, or can cause problems. There's some question over odor with vinyl ethers, but actually cured cationic films don't have a long lingering odor. There are two types of cationic initiators. One is a sulfonium salt, and the other is iodonium. Previously, sulfonium salts had a little bit of a question mark due to the fact that they were the ones that considered to release benzene. So a lot of people avoided them. But the BASF product I put on the screen is one that definitely now doesn't have any benzene problem and is perfectly suitable for food use. The second class of photoinitiator, iodonium salts, they are perfectly reasonable to use, and the odor doesn't last, but they do have a distinct initial odor straight after cure, which puts some people off. There's no real fundamental reason for not using cationic curing.
Thanks, Paul. Next question. Someone says, how can post-cure behavior be avoided in cationics?
Interesting. Actually, I'm not sure quite what that means. The post-cure is a behavior that you will get, and I presume by that refers to the fact that the reaction carries on long after the coating has come out from under the lamp. Typically, coatings are dry, touch dry, at the point they come out from the lamp, but they can carry on reacting for 24 hours. And that's normally seen as an advantage because it means that there's no unreacted fragments left in the coating. If it's a case that you just want to speed things up, sensitizers can be used. I hope I've got the essence of the question there.
I'm sure you did, Paul. That's about all we have time for, actually. Did you have anything to add before we conclude?
I'd just like to thank everyone for joining us, and I do hope that something good has come out of that. Obviously, talking to so many people in such a short time means that we probably need to contact later if anyone wants to take up any of the points here, and we can go into more detail. And thank you, everybody.
Excellent. So that just leaves me to thank Paul for what was a great presentation and to thank Perstorp for sponsoring this session. For the attendees, you'll receive an email shortly telling you how you can access the on-demand version of this webinar, or you can access this to our website, which is www.business-review-webinars.com. Once this webinar ends, today's survey will appear in its place, and we would appreciate it if you answer the questions in there. And we look forward to sharing further webinars with you, so please do keep an eye on the website just mentioned and follow us on Twitter at BRWebinars for daily updates and join our LinkedIn group Business Review Webinars. Thank you once again, and I hope you all have a nice day.